So my name is Gordon Miller. I'm one of the co-founders of Oakwood Controls. We're one of the sponsors of the conference here. We were here last year. Thought it was a really good conference, so I basically told everyone that works with me, you got to go to this conference. So we've got a number of different people from different companies that work with us on site. So Oakwood Controls, just to give you a heads up, we're a small company, roughly 16, 17 people now, working in a few different locations. Most of our work has to do with, and we started our work working in the kind of a very different space than a lot of the talks you see here. You know, we're not working in this commercial enterprise space. We're working in the military sensor applications. So when you watch Zero Dark 30 or Active Valor or Discovery Channel, and you see all the new tech and all the new network technologies that they're using to get sensor data, that's the space we work in. And in particular, what we work on is kind of the plumbing, if you will. Right? You go to a nice new model home, you got those nice Kohler light sink fixtures, right, that are all sexy and all that. Well, it doesn't do you any good to have this nice fixture for water in your shower if you don't have the plumbing behind the walls to get it there. We work on plumbing. So in particular, we're focused right now on a project for the Army out of Fort Belvoir. Well, it's a national program to define, and there's buzzword, dynamic, secure, networked interoperation between what we call terminal consumers and producers. So sensors and user interfaces to show that data. And then all the necessary supporting services. So we're trying to build service-oriented architectures on what's known as disadvantaged, intermittent, and low bandwidth devices. Most of the time, people dealing with consumer space get really upset when you have less than a T1 line, or we get upset when our Verizon line drops. I literally have to deal with places where 56 kilobits a second is good, and that's if it's not, and that's when it's working. So we're writing specifications. We also have to deal with integrating with lots of different groups across the nation, and they're writing in everything. They're writing in Java, C and C++, Python, Ruby, C#. The language is out there. We're having to deal with them. So what we've been involved with is writing kind of what we call a meta standard. If you go out and if you look at the IETF or IEEE, IETF is the big one, so IETF, Internet Engineering Task Force, they're the ones who own the standards or the specifications for things like HTTP and TCP and IP and UDP, SCTP, all of those networking standards that they own those. So what we're writing is a meta standard, which is a standard that uses those standards. And what we are then doing is, so I go off and I tell one set of guys, go write this, go up and look up the standards and go see what, according to paper, is supposed to be able to be done and how it's supposed to be done. And then I have another set of guys that I hand this poorly written document to, and I say, go make this work. And that's the verification. You can dream up all you want, but when you actually have to go cut code to it, you come to find out that things don't work as advertised. And for kind of the first time, we got permission we've been dabbling in Erlang, or I've been dabbling in Erlang for probably the better part of 7, 8, 9 years now. I'm a language junkie, always looking for the latest, greatest thing. And Erlang seemed to fit. So about a year and a half ago, I got my business partner interested in using Erlang. He thought it would work. So we convinced our government customer to use Erlang for this particular project. And what we've been able to do with it this year, we just finished up on the first year's effort, has been absolutely fantastic. So what I'm really going to talk about here is, I'm not going to get into too much code. I'm going to get into a description of the problem, get into some of the comparisons of Java and C and C++, how it's successful for us, how we've been able to sell it to the government. We've had a lot of traction. We're actually publishing a couple papers at some sensor conferences on using Erlang in these environments. So we got an interesting quote here. This was told to me in 2005, and this is something that they keep pounding into us when you're working with warfighters. And we go to the field probably 4 to 8 times a year to actually work with soldiers. These guys are typically, these are the ones that are trying to use the technologies in theater. These are guys who are frequently under fire. And the number one phrase is basically, an Army Sergeant First Class told me, if software dies in the field, people die. So high reliability is key. Okay, well what was Erlang written for? Erlang was written for high reliability distributed systems, right? That's one of the matchups that made this so appealing. You can write high reliable software in a lot of languages. There's nothing magical about Erlang in terms of what it provides. So the magic of Erlang is the philosophy, and then the OTP, and the fact that it lets you fail gracefully, detect it quickly, and then react so that your user perceived downtimes are very, very small. So we can't guarantee the software is not going to crash. Nobody can, right? The whole, you can't prove there's no bugs in code. But if it does crash, we want to back up in a time that doesn't react. So our service requirements are the software that we run and the platform that it runs on has to be able to run for days to weeks at a time, unattended. Okay, what unattended means is some soldier, a lot of times these are forward deployed units, so it's not like they have a lot of support, has to literally run out, potentially under fire or under observation, put a sensor in the ground and run back. Okay, if you have to do that 5-6 times a day, that guy's, he's at risk. So they want to leave these things out in the field for weeks on a time. That means that batteries are key. You got to be able to run on battery. And the heavier the battery, the more that soldier's going to curse you. If you tell him you've got to lug out a generator, he's not going to be happy. If you can give him a 9-volt and tell him that it runs on a 9-volt battery for a week, he'll love you. Again, the downtimes need to be in seconds. Minutes is unacceptable. Seconds is acceptable. Just as a point of reference, the thing that really facilitates this is it takes about, if you're at a forward operating base and you come under attack, it takes about 30 minutes for a support force to get to you. So if you're in Afghanistan or back when Iraq was a big focus, 30 minutes was the time period. So if a forward operating base came under insurgent attack, you had to keep these guys alive and their sensors had to work for 30 minutes. So seconds is okay. Minutes is unacceptable because then you're getting into a significant percentage of the time that they need these sensors. And the sensors are things like radars, video cameras. We're dealing now with fire control systems, things to launch the mortars, et cetera, et cetera. So in short, size, weight, and power are the things we have to care about. It's got to be modular. You ship the stuff out to the field, it may be a year before you get it back. And they want to be able, the soldiers are incredibly good. We primarily work with the Army, so I'm going to use the term soldier. They're very good at mixing and matching things. If you've got a box that they can turn on and they have some sense of what's coming out and what goes in, they'll figure out really cool ways to put this stuff together that you didn't even think about. As part of our development, and in fact we have to work with legacy systems, we have to deal with multiple presentation, session, and transport layers. I'll get into that. Runtime configuration is key, and your ability to get detailed runtime information. That's less of a key in field, in theater, and more of a key when we go out to do experimentation. So like I said, we go about 8 times a year, we do experimentation. We run this stuff, we're having soldiers use it. We want to be able to log in, be able to get detailed runtime information, memory usage, CPU usage, constriction points. I went over the meta standard. There are a ton of these, and the Army loves its standards. If you come up with a new system and you're not using an existing standard, you're dead in the water. You might get a little bit of funding, but you won't get traction. So you've got to tie this to existing standards. So we've got to be able to mix and match these things. And we've found some interesting, and you learn a lot of lessons about how they work together and don't work together. So real quick, I'm going to cover, so we've been doing this for about 10 years now under various guises, various contractors. So we've done implementations of these kinds of middleware, this kind of system support software, and basically these 3 languages. I've written some in OCaml and in Haskell, those were almost dead out of the box for some various reasons. So we're not going to cover those. But C++, you really can't go wrong with the government in that. They like C and C++. It's fast. It's got great tool support. You know, you can go out and pick up Visual Studio or Emacs. You can pick up libraries for everything. Creates the smallest executable sizes you need. Very fast. You can run it on any hardware. And if you're fairly clean about it, you can write moderately portable code. It is hard to write extremely portable code. When you start dealing with networks, and you start dealing with serial devices, and you start dealing with threading and those things, that gets tough to write. And there are groups out there, Boost, for example, will attempt to say that, hey, we've got standard libraries. I challenge you to read a Boost library and understand what it's saying. It's difficult. Any of your infrastructure support. So all of your things that are done in OTP that are kind of given to you, you're catching the system process dying and restarting it. You have to write all of that yourself from scratch. Again, Boost may advertise that they've got something. Boost got nothing good to say about it. And you have to recompile that per platform. We're really pushing the envelope down. We're trying to get to the point. Just to give you a point of reference, they're now working on and deploying Android tablets to individual soldiers in the field. So we're working down. We want to get that onto that Android tablet. We want that to be able to run for the soldier down there, the sergeant in charge of a small squad or a fire team. If you do an upgrade, you have to do a restart. That can kill you, especially when you're in the middle of a fire mission. We were out in the middle of a fire mission this past week doing some support. You can't stop that. They're in the mood of launching. They're in the mode of launching artillery. You can't. I got to stop you guys for a couple minutes. I got to do an upgrade to the code. I found a bug. It doesn't work. Okay, so Java. Java's fast. You can make fast Java code. Great tool support, but it's external to the Jdk. Okay, so you download the Jdk. You get a compiler. You get a profiler. Well, you don't even you get a profiler. It's tough to use. But any of the other tools that you need, any of your diagnostic tools, any of those are external. It is VM based. That's good and bad. The VMs for the Jdk are really targeted towards your Mac, your Linux, and your Microsoft systems. Your small embedded systems, you really have to go with the JME, the small edition, and that's a completely different architecture, completely different way of writing code than the SDK, the standard development kit. So they're really not the same. So the VM is really only available for big platforms. You can run it on the smaller platforms. We're going to get into that in a little bit. It is horrendous on memory. Horrendous. We're going to cover that in a little bit. I got a slide here just comparing some numbers for. The executable sizes are monstrous. When it compiles down to the bytecode, they're just monstrous compared to the equivalent Erlang. Again, the Jdk and restarts again are required. You can, in Java, if you know class loaders, you can build something up where it picks up that your class has been changed and reload the jar. But again, that's infrastructure you have to write. And every single system, was it OSGI, has a system for doing that, and it's glitchy and a pain to use, and so we don't like it. Erlang, it's fast. It's fast enough for our purposes. We have zero issues with it. Very good tool support within the distro. Okay, so the fact that I have within my Erlang, my OTP distribution, I have the compiler, I have all my tools, I have the dialyzer, I have my profilers, I have all the tools that I need to do the kinds of things that you do in plumbing work. They're all there within the distro. That's fantastic. I don't have to download additional apps. It's VM based and it's available on many platforms. We're taking advantage of the Erlang Solutions ports to. We just started using the Android port, the non-root Android port, which is our government customers got very, very excited about. Matter of fact, they put forth a whole new line of effort just to kind of see how this works on the platform. And the fact that restarts aren't required. I can't stress that enough. Our guy was sitting outside, they're running the exercise, he's changing code as they're doing it and loading it as the exercise. We found a bug, was causing logger, it was causing a process to crash. They just changed the code and fixed it, and they never knew the difference. It is very good on CPU and memory usage. The executable size is very small. And again, the support infrastructure is needed. I don't have to download anything additional. It's a big deal when you're dealing with the IA community. In the military, you can't put unapproved software on systems. So if you get a JDK approved, that's great. And you go tell them I have to get a new third-party add-on, it's a non-starter. They won't let you. But I go tell them I've got OTP, and they approve that. And in fact, we can get the source code for it. They're fine with it.
New JDK every other week for the latest book.
There is that, yes, and the Army, for example, or depending on the agency you're dealing with, you may not even be able to get 1.6. There's some agencies, or 1.7. There's still some agencies stuck on 1.6 because they haven't certified 1.7 yet, and they're very concerned about the move to Oracle purchasing Sun.
So this slide lists those things in front. I don't think they meant to have. What are the cons?
Oh, yeah, I didn't mean that. The cons are it's not very well known. That's the one con. I'm sorry, yeah, it's a good catch, thank you. It's not very well known. I had to kind of push for a little bit, for about 2 or 3 years to get Erlang accepted. I have the flexibility that my government customer, I don't know if he trusts me or just that he doesn't have anybody else he can go to. I don't really know what it is. But we wrote it in Erlang, and I kind of told him after the fact. I said, hey, we did this in Erlang. We think it's going to work. He said, well, you better prove it to me, and it better not fail because I'm going to fire you if it doesn't. False threat, but it worked. We were confident. And actually, he's incredibly excited about it. Excited enough that I haven't seen him this excited about an implementation, and this is unique, and we recognize it. As far as we know, we're the only ones in the Army using Erlang in this space. There are some, I think, that are dabbling with it in some other areas, yeah.
How small can you really go for the Erlang stuff where it needs to be like real time? Like how hard of a real time?
Okay, so in the Army, you've got two terms. You've got a hard, or in the military, you have hard real time, soft real time. Hard real time is your mission control, your hardcore like flight systems, safety systems, mission critical systems. I push a button to fire a missile, to fire a rocket. The military will say that needs to happen in a very strictly defined time frame. That's what's known as hard real time. If I detect a fire inside a tank, my temperature sensor has to turn on the fire suppression system within so many milliseconds, and it has to be provable. We don't have that. We're not in that particular space. We're what's known as the soft real time. So we can give you good enough. So we can get to example, if we're doing controlling a joystick, controlling a gimbal, turning a camera, we can easily get down to less than the human perceptible time frame. So 250 milliseconds. I think we did a study, it was like 250 milliseconds is the human perceptible when you're turning a camera, and we can get to that. I can't make it, we've done some measurements. We don't have hard real-time performance criteria.
Yeah, I'm thinking like audio range around 10 milliseconds. Okay.
Yeah. Now, in part of our stuff, we don't actually deal with, in the infrastructure we're developing, we're not actually we don't get in the way of video streams and audio streams and things like that. So some of the video processing and audio processing, there's a different, already established framework for dealing with that in the military that groups are already working on. So we're just concerned with command and the control of the sensors. That's a paraphrase of a quote that was given to me. Actually, the quote originally was, leave it to Scala to make something simple huge. We do a lot of work in Scala as well. And Scala is monstrous. So we're maybe regretting the decision to do Scala. Anyway, so here's just some basic numbers that I got off the, yeah.
Just a quick question. A couple minutes ago, it sounded like what you said was that OTP actually has, for the other folks that don't work with Army, that it actually has a certificate of networthiness?
No, it doesn't have a certificate, not an Army-wide. But since we can get the source, and since we can compile it ourselves, or we can prove that it came from a certified source, our accreditation authority has given us a stamp to use it in these environments.
I'd love to find out more about that because I'm trying to get my client to.
Sure, I'd be happy to talk to you after. So anyway, so these are some standard things. So because we go to the field, we want the full development environment. We got to do changes to code and stuff. Standard Jdk installation. This is the Oracle Jdk, 636 megabytes on the disk. That includes a compiler, the VM, and the necessary support libraries. I also felt it important to compare apples to apples. You can get a smaller, if you want just the JRE, you can install just the JRE and it's significantly smaller. When you do the when you run it, typically Java runtimes are going to want to grab about half a gig of RAM. At least the applications we're dealing with. Okay, so it comes up, grabs a big chunk of memory. That becomes an issue that's not a problem on laptops. Who cares about a gig of RAM or half a gig of RAM? You get into the small devices. So on the Raspberry Pi, which is right now is our target platform, the Erlang distribution installed, the full thing is about 132 megs. That's what, as of this morning, that's what my partner measured it out as, and that includes the compiler, the VM, and all the tools. We'll get into some of the memory stuff and what it uses in a little bit. So I'll tell you right now that on the Raspberry Pi, one of the guys that works with me, he controls the Pis. We've talked about putting Java on the Pi, and he just refuses. He will not even do it. He gets very angry. It's actually scary angry. Okay, so kind of enough about the bashing Java and the bashing languages. So I want to give you a real quick rundown on the 7-layer OSI model, which is how we're structuring our applications. Our specification, so for those of you who aren't familiar, this is a standard 7-layer OSI network modeling stack. It's a little different than what most people who write TCP/IP applications are used to dealing with. You got an application layer, presentation, those are various layers and what they do. So as we're writing our meta specification, we're actually writing it in terms of those 3 boxes and a little bit of the application layer, but in terms of those 3 boxes that I have surrounded by the dotted line. And what we're doing then is we need a mechanism to experiment with the various standards that exist already at those layers. And I need to be able to mix and match these. So I want to be able to say, hey, if I'm using this transport, and can I use this session with it and this presentation with it, and how do they work together? Okay, that was great. Now I want to change it. I want to use this. And so, so that's what we're dealing with. When you pass data between the processes, basically what you're dealing with is if I'm at the application layer and I have a chunk of data that I'm going to send, I push it down, and this is what ends up happening. As it passes through each layer either, if it's on the way out to the network, adds bits in front and bits behind, and each layer adds its own bits and adds its own bits. So you have at the network layer, which is your IP, you have an IP frame. If you're at the transport layer, which is TCP or UDP, you have a UDP frame. And so that's how these layers work. And so each layer has its own protocol. Okay? And if you go up and you download the RFCs, it'll actually show you the bits and the bytes that have to be in each of those preceding and the prepended and appended fragments of the frame. They'll actually tell, so TCP, you've got a timestamp, you've got an origin ID, you've got a destination ID, you've got a checksum, and it adds those to the beginning and the end of the frame, and so on and so on. And as it comes in, something comes in from the network, before it gets to your application, and most of this is done in your operating system, or some of this is done in your operating system, each layer reads its relevant header and footer, does what it needs to do, and either responds, does something to its internal state in the layer, or passes a message up, or passes a message back down. That's the way networks work. The OSI model is a lot more clear in their responsibilities. Some things about the layer interactions. When you write a layer specification, each one of these layers is unaware that there's a layer above and below it. So they're written to be completely isolated processes. Has its own binary protocol for interacting. So when I'm dealing with a transport layer, I'm actually writing a binary protocol that is supposed to interact with a layer on the other side. Again, what this is, so theoretically it allows me to do is write these composable layers. You can mix and match. If I need security, if I need encryption, I need authorization, I need compression, I can change out my session layer without, theoretically, without having to touch my other layers. This is why TLS and TCP work well together. I can run TCP or a non-TCP IP. The TCP layer, or I can run non-TLS or TLS. TCP doesn't care. Layers have their own state. Okay, TLS. Anybody here actually familiar with the details of the TLS specification? Okay, a couple. Right. So TLS has state associated with it. So packets come in, you do something with it, next packet comes in, and the processing of packet 2 is affected by the processing that happened on packet 1. So each layer has to have its own state. There may be time-based things. TCP, for example, needs to send out a resend request if it doesn't receive a message within a certain time. That's a function of TCP. It's got its own time-based event. So the nice thing is you've got a process, and just like if you've been doing Erlang for a while, and this morning, Erlang has these nice processes that are cheap to create. And what do processes have? If you use the Emacs Gen Server template, creates a thing, and the very first thing at the top you see is a record called state. And all the Gen Server does is mutate state as new functions come in and out. So already the Gen Server process model matches how one of these layers is supposed to work. It's a very clean mapping. And by only needing, each particular process doesn't need connections to the rest of the network stack. It just needs a connection to the one above it and the one below it. And it doesn't even care what it is. It's just going to throw across a blob of data. So when you go to write this in any other language, what do? And everybody right now is writing in OO, so I'm just going to refer to OO languages because only really old people now write just straight C anymore. But all the young kids coming out write, it's OO crazy. So what you have to do is, for every one of these protocols, you define a message set. And you go through the specification, you define an object for each message. And you define, so you have 20, 30 different classes. And then you have to define a base message class, so you have inheritance. And then you have to deal with a parser factory, and then maybe visitor patterns. And it just becomes a nightmare. I'm writing one in Java now, got about 15, 20 messages, and I had to create a whole new package, and the list of packages actually exceeds my vertical window height. I have to actually scroll. Very annoying. In Erlang, if you want to, you can define a client API. I've got the Gen Server stuff already done, so that's built in for me. So I just define a module for the layer that's a Gen Server. Define a single client API that already does handle info is my receive function. I use the bang operator to send the message to the next layer. The binary parsing of the messages, it's already there. And these are binary objects. This is not XML. This is, bit 1 means X, bit 2 means Z, So I use the binary stuff. The bit strings, that's actually what drew me to Erlang. I saw they had a bit syntax for unpacking, and I said, okay, I got to take a look at this. And you can put it all in one file. Now, some of the things we deal with protocol buffers, and that we use this thing called Peaky, and it generates a ton of files. So that doesn't always happen, but in general, you can. So just from a maintenance perspective, I can reduce my lines of code because I don't have to and I can reduce how many files that I have to span across to deal with it. Greatly aids. Yes, sir.
So you have one for receiving, one from below, one from above. What are you doing in Erlang code that you couldn't do in Java code?
Well, there's nothing you can't do in Java code, right? It's really the matter of how much I have to write in Erlang versus how much I have to write, and the localization. In the other languages, you tend to have to separate your parsing from your behavioral parts, and some might argue that that's a good thing because they're two separate areas of concern, but it increases your code size. You have to, is it a parsing problem, is it a behavioral problem, you're jumping files. In Erlang, because of the syntax and because of the way it works, you kind of put it all in one.
Because of the pattern matching?
Because you do the pattern matching and you're basically just using the function clauses to handle it. And so it's not that you can't do it in one versus the other. I think that Erlang just really simplifies your understanding and your ability to kind of know where a problem's happening, what I have to do to fix it. Okay. All right, so as I've been saying all along, the process model fits the network layer model extremely well. Processes behave independently, react to message events. I can use the timer module to set up. Timed events. And what we do then, kind of moving into, I'll cover that in a second. I'm going to move a little bit quicker than I am here. This is an example, kind of a contrived part where I've kind of very greatly simplified. But this is an example of kind of what I've been talking about with the ability, you put the message parsing in the function clauses together in with the behavior of what you do when those messages are received. So I've got a function, 3 clauses. Basically, they differ by what came in. So I can take a look at the bitstream arguments there and say, okay, and visually I can just take a look at this and say, okay, that's what I do when I get a request connection message. That's what I do when I get a change encoding message, and that's what I do when I get an application data message. It's all there. The parsing's there. If I get it wrong, if for some reason I deconstructed the bit string wrong, just change it right here. Don't have to go to another file, change it, and come back. It's all right there. It greatly aids in your understanding, and it's small and tight. So what we end up doing then is we create stacks of these things. So we'll take a presentation process, we'll take a module implementing a presentation layer, spawn it. We have a session and transport. Interestingly, even though the OSI model says that session and transport layers are supposed to be distinct, we tried that, and really they can't be. So we have to blend those into the same process. TLS does not work for UDP or SCTP, for example. You have to have DTLS for those. Nobody has DTLS defined yet, so you have to. So we lump those into one process. Our network is one process, and that should have been. That's the data layer. That's kind of the link layer, data layer below. That's not data. We put those behind a connection. The connection is a supervisor. It's not a supervisor in the sense. Thank you. It's not a supervisor in the sense of a gen supervisor because our restart strategy changes. But it monitors them, and if it crashes, if something crashes, it actually has to close everything up, cleanly close the connection, and then notify. So it's kind of it sounds like it's a one-for-all, but one-for-all will tend to restart, and we can't restart. We actually have to kind of shut it down and let another piece of the software handle that. But it's still dynamically configurable, and we still make use of the process links to monitor all that. So this is kind of a simplified model of the entire application. That little box we've got down below, that's just the same thing I just showed you. Top level controller, that's effectively your main. Some of the logic, and then a network acceptor that's receiving the connections, and then spawning these instances of the network stack. This is, at some level, fundamentally all we've written. It's kind of uninspiring when you look at it in a box diagram like that. Yes, we're going to move on. It's incredibly simple. So we talk real quick about our current deployment. This is where kind of the nice thing, and this is what sold us. We're running on the Raspberry Pi. It's an ARM processor. We have on those machines right now 256 meg of total space. 92 meg of that is consumed by the OS. That leaves 164 megs total for everything else we're going to install and run. Okay, so that's all your storage. You can see right there that Java's just not even going to fit, much less be able to run anything. So that's why Matt gets very angry when we even bring up Java and Raspberry Pi. So what about our stuff? Our previous implementation of this in C++, it took us about 7 or 8 years to develop, was 800,000 lines or more of C++ code. We've written it in 25,000 lines of Erlang in about 20 different modules, maybe a little bit more, maybe a little bit less. It's non-optimized. We've spent 0 time optimizing this. Unlike the C++, where we spent kind of 7 or 8 years optimizing it. Installed, it's less than 2 megabytes. That's the compiled code, the Beam files, very small. Last week, when we were down in just outside of Jacksonville, Florida, running this in some exercises on the Raspberry Pi, processing about at nominal loads of about 30 messages a second, which is kind of an average, not really hectic pace, we take about 8% of the CPU and about 7% of the memory on that Raspberry Pi. At 200 messages a second, we start to hit the limit of the CPU. We have maxed out at about 250, where the CPU actually starts dropping, just really can't handle the load. But for a 756 megabyte or megahertz processor that's literally power on, power off, powered by 5 volts, that can be powered by a 5 volt power source, that's pretty good. That's pretty good. And we don't see any other way that we could have hit that performance, either using Java at all, and then the time it would have taken to do that. We're pretty confident that if we, some back of the envelope, that if we sat down and actually optimized our Erlang code and actually went through, and we've done no performance measurements on this whatsoever, we found some, we think we can get it up to be able to handle about 300 messages a second through a single box. The system itself has multi-tiered, so we can actually distribute this if we need. But that's one machine, one Raspberry Pi, and was able to support an entire exercise for a few days down just this past week. In closing, right now we're the only group that we know of in DoD that's using this. We're in touch with most groups doing this kind of work for the military. We're the only groups using it. Our government customers are really excited about this, the prospect of doing this, the fact that the community is growing. And if you're trying to sell this to an existing government customer, what you need to tell them is that it's not a new language. Okay? They asked, it's been in use since the 80s, right? It's been well established. Ericsson's been using it for years. Other companies have been using it for years. Once you start getting them off of being first acceptors, and you say, look, you're not the first acceptors. You're just maybe one of the first you've heard of, and it's not huge in America, but it's big in Europe. It tends to take a little bit of the not me first that they want. And it's not the silver bullet. I mean, I can go on and on about the things that are bad about Erlang.
No.
Okay, but this is not the community for it because we all love Erlang. But for this particular space, it's absolutely been a great thing for us. So anyway, that's all I've got.